Welcome to Study Loop.
Okay, so for this question, we can determine the temperature at a test area by such equation here. So we have T is equal to T0 over 1 plus K minus 1 over 2 times MA squared. T0 here is the stagnation temperature, or not what the initial temperature. And we know K is the specific heat ratio for the air, and we know MA is the Mach number. So we know the temperature is given as 100 degree Fahrenheit, which is 560 Rankine. And the specific heat ratio is 1.4, and the Mach number is 2. So now let's plug in back to the equation to determine the temperature at a test area, which is equal to 560 Rankine over 1 plus 1.400 minus 1, and then divide by 2 times 2 to the power 2. And this will give us the temperature is about 311 Rankine. If we convert it to degree Fahrenheit, it's about negative 149 degree Fahrenheit. So now let's determine the pressure for the test section. So we have P is equal to P0 over 1 plus K minus 1 over 2 times MA squared to the power of K over K minus 1. So we know the stagnation pressure, or the initial pressure, is given as 150 psia. So now let's plug it back to the equation to determine the pressure at the test section, which is equal to 150 psia divided by 1 plus 1.4 minus 1 divided by 2, and then times 2 squared, and then to the power of 1.4 over 1.4 minus 1. And this will give us the pressure at the test section is about 19.17 psia. And then let's determine the velocity at the test section, which is equal to Mach number times square root kRt. So we know R here is the gas constant for the air, which is about 0.06855 British thermal units per pound mass times Rankine. So now let's plug in back to the equation to determine the velocity, which is equal to 2 times square root 1.4 times 0.06855 British thermal units per pound mass times Rankine, and then times 311 Rankine. And now let's convert it to v squared per second squared under the square root, because the value, the units for the velocity is v per second. So this will give us 25,037 v squared per second squared over 1 British thermal units per pound mass. So eventually we'll have the velocity at a test section is about 1729 feet per second. So now we can determine the mass flow rates. So the mass flow rate is equal to density times the area and then times the velocity, which is equal to P over RT times A times V. So we know the pressure at a test section, and the gas constant for the air can be also expressed as 0.37404 psia times V to the power 3 over per pound mass times Rankine. And we know temperature is 311 Rankines. And we know the area is given as 5 v squared, and the velocity is 1729 feet per second. So now let's plug in back to the equation to determine the mass flow rate at a test section, which is equal to 19.17 psia over 0.3704 psia times feet to the power 3 over pound mass times Rankine, then times the temperature, which is 311 Rankine, and times the area 5 v squared and then times the velocity, which is 1729 feet per second. And this will give us the mass flow rate is about 1439 pound mass per second. Okay, so the reason why the air must be very dry for this application is because the temperature at the test section, which is T here, is really low since it's equal to negative 149 degrees Fahrenheit. And also the pressure is really low as well. And we know the pressure is about 19.17 psia. So it's because they are very low. So therefore, at this temperature and pressure, whatever water particles available in the air are in the ice phase only. Okay, and that's why the air must be very dry for this application. And these are the answers for this question.